It's a great pleasure to have Philippe Robutel today that is going to speak about TOI-178 from a hypothetical co-orbital system to planets in Laplace resonant chain.
Thank you. So in when was it? It was in August. In August 2018, TESS observed the star TOI-178. So TESS is a NASA mission designed to monitor about 500,000 nearby stars and focus on Earth and super-Earth size planets. So I don't know if you can see the, no, it's not here, the pointer here.
Yes, we can.
Yes.
Okay, good. So as you can see here, the telescope monitors the brightness of the star on, as you can see here, when a star transits the disk when a planet, transits the disk of a star, it generates this typical curve, this dimming on the light curve. And if this phenomenon appears periodically,
Adesso, cioè, che cos'è molestia, che cosa è accettabile, cioè, questo tipo di cose, no? che magari sembrano un po' banali, forse da dire nel 2021, però forse no, perché insomma,
Marco, you should
of the planet, and at least its orbital period, on its inclination, on the line of sight, on its radius, at least. So, as I said, the TESS observed the star about 2 years ago. It's a quite small star. You have the details here in the south hemisphere in the constellation of the Sculptor. So, you have here the light curve of the stars with two kind of dots, the data in small dots, and in white or black circles the beams data. And this observation is 27 days long without interruption, just maybe a little one here, but okay. So you can see sometimes dims in the light curve. So of course, the TESS reduction pipeline assigned these events, this dimming in the light curve, to planetary transits with a very high level of confidence of about 95%. So here, these 4 transits are assigned to a planet with orbital period of more than 6 days, here 6.55. Here, these 3 transits corresponds or assigns to a planet of orbital period about 10 days, and the last one, these two transits here corresponds to a planet of a period of about 9.9 days. Okay. So we are left with this kind of data. So we have the periods, which are with a good determinations, and then the radius here and there of the 3 planets, and the radius are poorly constrained, of course, because we have only a few transits, but it is very unlikely that we have the mass of the planet are lower than 1 Earth mass. So we deduce here from the time of transit, what are the mean longitude of the planets. So we have the inner planets here and the 2 outer planets. So they are practically on the same orbit. And here, from the time of the transit, we can deduce that this configuration is not far to an equilateral triangle. Okay, so if we compute the ratio of the orbital period, we are very close to 1. So maybe these two planets here, the two outer planets, are in 1-1 in motion resonance. So perhaps we have co-orbital system here. The third planet here, the inner planet, is also close to a mean motion resonance, the 3-2, with the two outer planets here. You have the ratio of the periods here. So this make this system good candidate to our co-orbital planets. Okay, what are co-orbital planets? So, or co-orbital systems. That's very well known in the solar system. For example, the main example corresponds to the Jovian Trojans. Here, so the configuration correspond more or less to an equilateral triangle with some oscillation with a long period, but it's more or less something like that. You have another very nice example of a co-orbital system in the solar system that corresponds to the small satellites Janus and Epimetheus around Saturn, that describe in rotating reference frame horseshoe orbits. So it's a very long, very large amplitude of libration around, okay. And then you have few examples, other example of the kind of configuration, quasi-satellites and so on in the solar system or also. So about co-orbital exoplanets. This planet should exist. They may, if we look at theoretical works concerning the formation of the planets, the co-orbital planets may exist and may be a byproduct of this planetary formation. I mean, you have a lot of papers that describe this phenomenon, but to date, no co-orbital exoplanet or co-orbital system has been observed. Why? In fact, it is very challenging to detect co-orbital exoplanets. There is many different reasons. So the best case is the case when you can see the two planets. For example, you have transit of the two planets. So yes. So the two planets transits the star. So it's the ideal case. You can measure the difference of longitude between the two planets, and planets. You can have the periods and so on. So we thought it was the case for TOI-178. So it's an easy case. So more difficult. We assume that you are only one planet transits. So it's the case in two different situations. When we have a small planet, when the planet is too small to generate observable dimming in the light curve. So for example, here, this one transits, this one too, but we cannot see the transit. And another case, when you have mutual inclinations, just a few degrees is enough between the two planets, this one transits and this one not. So in this case, we can eventually do something. We have two different situations one more time here. If we can see transits of the planets, and if we have time transit variations. If the motion of the planet is Keplerian, the time spent between two consecutive transits is always the same, it's constant. If you have perturbation, so due to other planets, for example, the time span between the two consecutive transits varies. You have a nice example here of variation of the time of mid-transit here. So in this case, you are sure if you see that the there are other planets that perturb the system, the planet that transit, but the problem is very degenerate in this case, and it's not clear that you can find the right solution of the problem. It can also be, if you have only one planet, it can also be generated, this kind of signal, by a moon satellite of this planet. Okay, you have another very interesting case. It is when one planet transits, and when you have the radial velocity, you can measure the radial velocity of the star. So, okay, it's the reflex motion of the star due to the existence of the planet. So, just to make short, we assume that we have two planets, the star on two planets, co-orbital planet on the same orbit, and that the orbits are circular. Okay, so we have the transits of the red planets, and we can measure the radial velocity of the star. So when the star here is the center of mass of the two planets, so when the center of mass crosses the line of sight, the radial velocity of the mass of this point, of the center of mass of the two planets, is perpendicular to the line of sight. So it's the same thing for the radial velocity, for the velocity of the star. So the radial velocity is equal to 0, but the flux, the light curve, is always constant because nothing transits here. Then after the second, the red planet transits here, the star, and then you have this decrease of the curve of the light, of the flux, and then you have a delay between these two events. So it can be this delay can be related. It can indicate the presence of co-orbital planets, and can be related to the mass of the planet here and to the difference of the mean longitudes of the body. Of course, it's a very simple situation in this case because the planets are assumed to be circular. So we have developed a method to get rid of the problem of eccentricity. You can see the details in this paper. Okay, so on the last case, we don't have transit. We only have radial velocity, and maybe it is possible to deduce that we have co-orbital system. So we have different situations. In the first situation, we assume that the two planets are very close to the Lagrange equilibria, the equilateral configuration. And in this case, the signal in the radial velocity generated by these two planets is exactly the same as the one generated by only one planet in Keplerian motion. So you cannot detect the co-orbital system. In the contrary, if you have large amplitude of libration, so the relative motion between the two planets have a very large extent, as it's the case in the horseshoe situation here, you can see it generates modulation on the radial velocity. Something like this. Here it's an example. So you have the radial velocity here of the star, the time, and then the curve of radial velocity here with two periods. The short period corresponds to the orbital period, and here you have a modulation here that is associated. It corresponds to the period of libration of the motion between the two planets, co-orbital planets. Okay, so if you can measure this amplitude on the period, so you can prove that you have co-orbital planets, and then you can have information about the masses of the planets. But it's not so simple, because to be in the favorable case to observe radial velocity modulation, the two planets must have a very large amplitude of librations. The two co-orbital must have comparable masses, and you must have a lot of observation to detect this modulation. So it's not something you can see every day. Okay, so we have our system here. So with the 3 planets, 4 transit for the inner one, 2 for this one, 3 for that one. Okay, and then we can assume that we'll study just a little more this case, the case when we assume that you have co-orbital. So just a few words about the co-orbital dynamics. So here, assume that we have elliptic elements. We can use a Poincaré variable, for example, to describe the Hamiltonian of the problem. So the capital lambda is related to the mean motion. This one, x, is related to the, what's the name, the eccentricity vector here. And then the Hamiltonian can be written as the sum of 2 terms, the unperturbed, the Keplerian part on the perturbation that corresponds to the interaction between the planets. So we have a small parameter here with epsilon, which is the sum of the two, the mass of the 2 planets divided by the mass of the star here. And of course, this perturbation here is small with respect to the Keplerian part. And then we have another, the angular momentum, which is constant, of course. So to study this problem, we can start by defining two values of the action for which the 2 Keplerian orbital frequencies are the same. It's here what we done. The Keplerian frequencies are there, and then we can define these 2 quantities, such as these 2 values are equal here. And then it corresponds, once we have this value, we deduce the semi-major axes of the two planets, which are quite more or less equal. The ratio is equal to 1 plus something small that tends to 0 with epsilon. Okay, and then we will work in the neighborhood of this these 2 lambdas, initial lambda. So, okay, here it's the difference of the mean longitude. Of course, as we are in co-orbital motion, the 2, say, Keplerian mean motion of the 2 planets are always close one to another, to the same quantity. So this variable evolves slowly with respect to this one which corresponds to the orbital motion of the planet, one of the planets. So we can average the Hamiltonian with respect to this quantity. It's very usual. So we can, in a given domain of the phase space, I will not enter into details here, but you can transform your Hamiltonian to its average here and a remainder, of course. And then you have, in this, you have the angular momentum, which is constant, that corresponds to this quantity here. So the angular moment, so of course, Z2 is constant. Now, if you want to expand the Hamiltonian in terms of elliptic elements, or for example, in power theory of eccentricities, so you have this kind of expression. And the important thing is that due to the constants of the angular momentum here, which corresponds, which is equivalent to the invariance by rotation of the problem. So we can prove very easily, that's one D'Alembert relation, that this monomial, the degree of this monomial is always even. So as it's always even, so you can expand the Hamiltonian in terms of elliptic elements, then you have this kind of things, polynomial in Poincaré variables with coefficients that depends on the angle here on the variable z. And this due to the existence of this integral, it's very easy to show that, to prove that the degree of this monomial is even always. So as it's the case, the manifold x1 equal x2 equals 0 is invariant by the flow of the average Hamiltonian. So you can study the dynamic in this plane. So when the two eccentricities, average eccentricities, are constant. Yeah. So the Hamiltonian in this manifold reads like that. So the Keplerian part, the perturbation. Here you have the mutual distance between the two planets. Zeta 1 corresponds to the angle between the planets. Okay. And then you have first an integral in this plane, Z2. Then here the phase portrait. So now you see the phase portrait. Okay. Here in the x-axis, it's the difference of the mean longitude of the planet, so the angular distance between the two planets. And here the variable z1 that corresponds to more or less to the semi-major axis. In particular, if you are on that line, Z1 equals 0, the two semi-major axes are equal. Here, when Z2 is negative, no, Z1 is negative, the A1 is smaller than A2, and so on. So, for example, if you follow this curve, this trajectory, you start, for example, here when the planet 1 is the outer one, and then the two semi-major axes are equal, and after the planet 1 is the inner one, and so on. So they exchange the orbits. Of course, you have fixed point, at least 3 here, maybe more. These two fixed points correspond to the circular Lagrange configuration, the equilateral configuration. Around you have libration, so you have a periodic deformation of this configuration that in this region on this one that corresponds it's the region when the Jovian Trojans are, and you have here this fixed point, the unstable one that corresponds to the Euler configuration when the two planets are on both sides of the star. And then now here in red, the red regions correspond to the very large amplitude of libration. For example, the horseshoe orbits where Janus and Epimetheus are. And the gray region is the outside of the resonance, of the co-orbital resonance, of course. So this region, the Tet-Pole region, on the horseshoe regions, the width of these regions depends on the small parameter, the ratio of the planetary masses by the mass of the star. So here it's the square root of this epsilon, on here epsilon power 1 to the third. So it depends on the planetary masses. Just a remark, in this phase space, you have this point here, it's the same one. These points corresponds to the collision between the two planets. And here you have a collision region here where the average Hamiltonian is no more valid, because if the distance between the two planets is larger than epsilon to the one third, the perturbation, the remainder is smaller than the perturbation. And then in this region, it's not the case. So the average problem will be valid in this region and not close to the collision region, of course. So let us return to our problem. So assume that we have only two planets in the TOI-178, not the inner one, the two which are supposed to be maybe co-orbital. So here, it's the result of numerical integration with the initial conditional, this one, the planet, the initial eccentricities are equal to 0. The difference in longitudes are equal to these quantities. And then you have two axes. Here you have the ratio of the initial orbital period, which correspond to the ratio of the semi-major axis, the initial semi-major axis. And here, the logarithm of epsilon. So because we don't know what are the masses of the planets, but what we know is that the P1 divided by P2 is equal to 1.004. So we are somewhere on this line here. Okay, so when the ratio of the two mean motion is far or not too close to 0, we are outside of the co-orbital region. And here we have stable motions with gaps here that you can see in gray that corresponds to unstable region generated by mean motion resonances, of course. And then as the ratio of the orbital period tends to 1, these mean motion resonances accumulate and generate huge unstable chaotic regions here. And then if you are very close to 1, depending on the mass ratio of the mass of the planets, you enter in the co-orbital region here. And then this, so here in yellow, you have the offshore region, and here it's the tadpole region when the equilateral equilibria is along this line. Okay, so where are the planets in this picture, on this picture? So we don't know exactly what are the mass of the planet. We can assume that the minimum mass is somewhere here of the sum of the two planets. So here we are in the outside of the co-orbital resonance in a very unstable region. Now, if we increase the mass, no, it's here, the mass of the two planets, here we are, for example, here, because the width of the co-orbital region, which depends on the mass ratio, increases, and then the system falls in this region here, in the offshore region. And then if you increase more the mass of the planets, you fall in the tadpole region, of course. So we are somewhere here. So, okay, we can assume that we are on this line. And then now we can take into account the third planet. So I will not enter into details, but I've shown before that this planet was closed to 3-2 mean motion resonance with the two potential co-orbitals. And then this closeness to the resonance, this resonance, generate chaotic regions associated to secondary resonances. So secondary resonances are resonances because between the combination of mean motion that you have here and the frequency, the libration frequencies of the co-orbital. In other words, it's the frequency of the motion between the relative motion between the two co-orbital planets. Okay, on this plot. So in this plot, on this plot here, you have the epsilon, the sum of the mass of the two planets here, like there, but it's not the same scale here. And here, it's another dimension. It's the mass of the inner planet. And then the co-orbital region is there, here, the unstable region that you can see here, and you see these gaps that corresponds to the secondary mean motion resonances. But despite the this inner planet, there is still room for stable co-orbital motions here and here, for example. Okay. So just another point, with this this unstable region, we can deduce what is the minimum mass of the planet. If the sum of the masses, if the sum of the planetary masses is lower than this quantity, the system is unstable. Okay, so we have a lower bound. So, co-orbital planets or not? So we cannot conclude with what we have. We have only for a few transit of the planets, and then we don't know what are the masses. So maybe it's co-orbital, maybe it's not. Okay, so we need additional observation, and it's what we have done with two kinds of observation: photometric observation here, so transit, the light curves, with speculoos and with NGTS, and spectroscopic spectroscopic observation, so the measure the radial velocity of the star. Okay. And then we have at these two dates, 1 year after test observation, observation of transit of the light curves. So if we assume that the planet of the planet 1, the planet with 10 days of orbital period is in Keplerian motion, we can assume that it's the case. If we do this, we can compute ephemeralities of the system and then deduce the date of transit of the planet. So we can do it and observe the star at this moment. So we have these two dates here. So in October, okay, we have transit of the planet, and here we don't have transit of the planet. So is it a problem? Not really, because of course, if the planets are co-orbital, there are interactions, strong interaction between these two planets, and this interaction generates TTVs. Here you have two simulations of this, of what can be these TTVs. For example, in this case, the red curves correspond to the TTV of this planet, the 10 days planet, and you see that you can have TTVs of amplitude of 2 days here. So between these two different dates, the TTVs, if we trace this curve, are of about 6 hours. So 6 hours, if the planet transit here, in this case, in September, it should transit there or there, so during the day. Okay, so it's still consistent with the co-orbital hypothesis. And then if we study if we reanalyze this test observation and if we had expressors radial velocities observation, it started to show sign of additional planets. A planet of period about 1.9 day, another 3.2 day, and maybe something else of period about 15 days, but it's not very clear because maybe it's related to the rotation of the star. Okay. So to conclude, we need additional observation one more time. What we can do if we observe the star during 11 days at least without interruption, we will show at least 2 transits of these 2 planets during 1 day, 11 days. So it's we can do. It's possible to observe during 11 days with CHEOPS, this new satellites here. But it's not very easy to convince. It was very difficult to convince the CHEOPS team that the observation is very important and to dedicated 11 days of telescope only on this star. But as the discovery of the first co-orbital planetary system would be a very nice result, it was possible. And then here in August 2020, so 2 years after the observation of TESS, CHEOPS observed the planet, the star, and get this. Sorry, it's here. This light curve. Okay. So here is the light curve. On it is a model of transit here that is fitted to the observation. Then, of course, you can see that you have a dimming in the light curve and small phenomenon on other one. Okay, so this very small dimming are assigned to the planet here with a period of about 1.9 day. The other new planet here with 3.4 days here for 3 transits of this planet, and then the planet that we knew, this one at 6 days, 6.4, the inner one of the previous discussion, that transits here and there. Good. But the problem is that we have only this transit left, and we have only 1 transit for 2 planets, the 9 days period and the 10 days period. So the co-orbital hypothesis is not the right one because we have only 1 transit. So this transit here, does it correspond to the 9.9 period planet or to this one, the 10.3? Okay, to know it, it's not very difficult. Sorry. It's there. So, no. Mm-hmm. Okay. No. Good. So we are not, now we know that we have not co-orbital planets. So we have no reason to have very strong TTVs because the interaction between the planets are not very, very strong, probably. Less than if we have these 2 co-orbital planets. So if we assume that the motion is close to Keplerian motion, this planet, the 10-day planet, should have transit in September, and it's not the case. So this planet did not exist. So we have one planet, probably the 9 days here, and not this one. Good. So if we return to test transit, so we have the transit of the 6-day planet here, this 4-1, the one of the 9.9 planet, these two here, and then we have these 3 transits that were assigned to a 10-day planet. Okay, so what we can do, the straightforward solution is to assign this 2 transits, the 1 and the 3, to a planet with the period with period twice of the expected quantity here. So the 10 days planet. So we have these 2 transits here with the 10-day planets. Okay, why not? So as we have done before, we can check that it's the right period by computing ephemerides of this planet with this hypothesis and to observe the transit of the planet. So we can we have this date for the transit, and then Cheops observe at this date, around this date, and then okay, the planet, the 20 days planet was there, is there with the transit of the another one. But okay, so it's the right hypothesis, but the problem is this transit. Here we have something, probably a planet, but something else. We have to find what is this planet. So we have this this system for the moment. So we have 4 planets, A, B, C, D, and this one at 20 days. If we compare the orbital period of these planets, we can see that these planets are very close to mean motion resonances. The 2 consecutive planets are close to mean motion resonances, not exactly, but not far. Okay. And then we have more. If we compute the mean motion, and if we compute this quantity, so the combination of mean motion of 3 consecutive planets, not the B, but C, D, E here, and D, E, G here, these combinations are very close to 0. So it corresponds to Laplace resonances with these 3 pairs on these 2 pairs on these 2 one. So Laplace resonances, it's well known in the Galilean system, the Galilean satellite of Jupiter. So Laplace notices that the mean motion between the 3 innermost Galilean satellites are in 4-to-1 commensurability. And then if we compute the difference, if you look at the difference of this linear combination between the mean longitude of these 3 satellites, you have oscillation with a very small amplitude, less than 1 degree, I think, around the given values. Okay, so you can easily generalize this resonance, Laplace resonance, to multiplanetary systems. And in our case, in our situation, these angles, this combination of mean longitude oscillates around a given quantity, and this one too. So we have 2 Laplace angles that maybe that librates. We'll see it later. Okay. So we have this resonance chain. So we have a mean motion resonance between the planets with three consecutive planets in the system. And this kind of resonance chain is not here by chance. It's generated by some physical process. For example, one very well-known process is the migration of the planet in the gas disk before the disk evaporates. In general, it generates a chain of mean motion resonances. And then we can assume that the planet, the hypothetical planet F here, is a part of this resonance chain. And then the simplest way to put it in the resonance chain is to assume that we have mean motion of order 1 between these two planets and of order 1 between these two ones. So for example, the 3, 2, the 4, the 4, 2, 3. And then starting from this hypothesis, we compute we can deduce the period, orbital period of the planet F, so close to 15 days. Okay, so as usual, with this hypothesis, we can compute ephemerides of the planets and then observe at the moment of the predicted transit. And that it's the fourth observation of Cheops here, and then it corresponds to the transit of this planet, and also the transit of the inner one. So good. Now, yeah. So we have 6 planets, sorry, and then each. Now, if we look to the test transits on Cheops 1, each transit is now assigned to the right planet. So here you can verify that you have the right planet. Okay, so no co-orbital system, but a system with at least 6 planets. So we, of course, assume that the orbits are circular because we cannot get the eccentricities of this planet. We'll see that the eccentricities are small in a few minutes. So we have the orbital period of these planets here, semi-major axis, the radius of the planet. So it corresponds to super Earth, 2 to 3 times the radius of the Earth. The masses deduced from an assumed density, but constraints also by the radial velocities observations here. And we have the inclination here on the light of side, and then we can see that the system seems to be very close to be planar, very close to a planar system. Okay, and then we have this closeness of this mean motion resonances between the planets. Here is the the system. Okay, so the system is embedded in a Laplace resonance chain here, and then we can deduce here the 3 Laplace angles with 3 consecutive planets, so C to E, D to F, and E to J. And then this quantity vary slowly around a given value, specific values. Okay, so now what about the stability of this planetary system, this system with 6 planets? So here it's a stability map here of the system. So deduced from numerical integration, of course, long-term simulation. So we start with nominal initial condition, the one given in the previous table. We assume that the eccentricities are equal to 0 and only vary the orbital period of the planet F here of the eccentricity of the planet F. So red correspond to chaotic motion, and here dark blue to very stable motion, very close to quasi-periodic motion, though stable for a very long time. So you see that here it corresponds to the region where the planet F is here. So inside a very regular region, if the eccentricity is small. So you see that you have a red region that corresponds to mean motion resonances between the planets and some islands of stability. So from this plot, we deduce that the eccentricities of the planet, or at least F, but it's the same thing for all the other planets. So we can do the same kind of simulation. So the eccentricity of the planet must be very small if you want that the system to be stable for a long time. On here, if you make simulation, numerical simulation, very long time numerical simulation with the initial condition close to the nominal one, we deduce that in fact the eccentricities do not exceed 100 about. So this condition of stability seems to be fulfilled with the system with nominal initial conditions, or nominal conditions, and very small initial eccentricities, 0, for example. So the orbits are almost circular. Okay, another section of the phase space, just to have an idea of where are the resonances in this system. So here we have, so the initial conditions are the nominal one, except for the period of the planet F or on of the planet G. So here you have this blue region, which corresponds to a stable region where the system is here, and this region is surrounded by chaotic region generated by overlapping of mean motion resonances. So here we can deduce what are these mean motion resonances. So, for example, the horizontal line corresponds to mean motion resonance of I order with planet E and G, the vertical one to resonance with E and F, and the oblique lines, the inclined lines here, unstable structures, correspond to Laplace resonance, mean motion resonance between E, F, and G. Okay, and you can see that you can look at the scale here. So if you change just a little bit the initial condition, less than 0.1%, the system falls in unstable regions. Okay, about the angle, the libration of the Laplace angle. So we have these three Laplace angle, and then we can start with the nominal initial condition and then numerically simulate the variation of this angle. And then you see that these three angles are librates around given values, with combination of period that range from years to several decades here, but we can not exactly know what are the amplitude and what are the frequencies of this variation, because it depends very strongly on the eccentricity, on the values of the eccentricity of the masses of the planet. So if we change a little bit the initial eccentricity, we'll change this period and we will change this amplitude of libration very on the same thing with the masses, which are not very well known. Okay, so now, just to have an idea of the extent of the resonant chain versus the mass on the period of the planet F. So here you recognize a stability plot. Here it's the period of the planet F here. The planet is assumed to be here. And here the mass of the planet F between 1 to 10 Earth mass. Okay. So the planet is in this very stable region. And this plot here corresponds to, it's the same initial condition, of course, but here the colors correspond to the number of Laplace angles that librates. So among these three Laplace angles, 0 to 3 angles can be in librations in these regions. So if we start here along this line, you see that correspond to the yellow region where the 3 angles, Laplace angle, are in librations. So these regions, the region when the 3 angles where we have the full resonant chain does not seems to depend very much of the mass of the planet F. And it's the same thing for the other masses of the other planets. But if you change just a little bit the semi-major axis or the orbital period of the planet, here it's 0.040 days, you fall in this red chaotic region, and in this region that correspond to these 2 regions, no angle, no Laplace angle are in libration. So you are in chaotic region, and you are the resonant chain is completely broken. And then if you enter in this region, the blue one here, if you increase a little bit the orbital period of the planet here, the planet F, you have a very stable region, but only 1 angle which is in libration. Of course, it's this one. Okay. So on this, in this region, it seems to librate independently of what the mass or what the orbital period of the planet F is. Okay. Good. So now some comments. The first one is that, as we have seen, as long as the system is in the full resonant chains with 3 Laplace angles that librates, it's the case on the neighborhood of the nominal initial conditions, the system is stable for a very long time. Okay, but as I said before, a mechanism, a well-known mechanism that can trap the planets on resonant chain is the migration of the planetary systems in the gas disk. So the problem is that, so you have in general a smooth migration in the gas disk, and then that leads to a chain of resonant of planets that are trapped in mid-motion resonances. But the gas evaporates. So when the gas disappears, the interaction between the planet, the gravitational interaction, are no more damped by the gas. And then you can have large eccentricities and so on. So you have 2 solutions, 2 consequences. Some of these systems, in some case, but it seems to be not very often, the system remains stable, and then it remains in the initial resonant chain, or the system is chaotic, and then this chaos, this interaction can lead to collision between the planet, ejection, and eventually rearrangement of the planetary system. For example, an inner planet can be transferred to the outer part of the system. So in this case, we don't have resonant chain, of course. So it seems that with TOI-178, we are in this case, because now the gaze have disappeared and we are in this resonant chain. Okay, so now if you look at the density, because we can we have an idea of the density of the planet, because we have the constraints on the masses of the planet, and then we have the radius of this planet. So in general, theoretically, the density of the planet decreases with the distance of the star. So here we have example of 4 systems, planetary systems, that are known to be in Laplace resonant chain. So in these 4 examples, you have this hypothesis is fulfilled. So the density decrease with the distance to the star. Here you have rocky planets, Earth-like density, and here something like Neptune or something like that at the end of the system. But for TOI-178, and in particular for the planet E and F, no, yeah. Here, it's absolutely not the case. Here you have a rocky planet, Earth mass density. Here, 2, and here you have 2 Neptune-like planets. So it seems that it's difficult to explain by current planetary formation this kind of situation. And then more likely, it should be due to chaotic phenomenon, giant impact or so on. So it's in contradiction with the previous arguments. So we have something to explain in this system. Another comment about the planet B, the inner planet. So this planet is not, or no more, is not in the resonant chain, not far to the resonant chain, but outside of this resonant chain, though the question is to know why is this planet outside. Maybe it started inside the resonant chain and came out through a tidal dissipation. It's something that have to be checked. And last comment, or the planet, maybe the last planet is the planet of 20 days period. Then maybe there are other planets with longer orbital period. But here it will not be easy to prove, because due to the small inclination, we have seen that the system is quite more or less planar, but the inclination on the line side is about 1 degree. And then if the planet is too far from the star, it does not transit. So we only have a radial velocity to detect this planet. So it will be very long and not easy. And then the upcoming observation will tell us more about this system. And if just you want more details about what I said here, you have these 2 publications about this system. Okay, so thank you.
Thank you very much, Philippe, for the very nice presentation. And are there any questions? Any question or comments?
I have a couple of curiosities.
Yes.
Okay. Well, bonsoir, Philippe. Hein?
Bonjour.
Well, first, I checked the date.
Yes.
The last time we met, and it was in Bad Gastein, and you presented a nice talk.
Yeah.
About a way to try to hunt, to recognize co-orbital planets.
Yes.
And so this was a different perspective with respect to that you described in the first part of the talk.
Yeah.
In the sense that, okay, you had to guess the kind of observations you could have.
Yes.
While in this case, okay, starting from real observations that seemed to be coherent with the hypothesis of co-orbital planets, you made a further analysis. So first, I guess your project helped you during these preliminary phases of the analysis. And is it true? And second, well, what about that project? Is still going on? I remember you asked for observational time.
Yes.
And so did you find something? Or?
No, of course not. We have candidates, good candidates, but for the moment we cannot conclude because we need additional data.
Okay. And another curiosity, and that's it.
Yeah.
As far as I understand, when you performed a stability analysis, okay, through frequency analysis and so on and so forth, you integrate the complete equations of motion.
Yes.
I mean, it is not an averaged model with respect to the fast angles. It is not an average model with respect to the libration angle.
No. It's the full system. Yeah.
Yeah, because I'm curious to know what an averaged model could tell about that system, but okay.
Yeah. It's a good question. It's what we are trying to do now to compute to use average system and to try to compare the result with the numerical simulations.
Okay.
So
thank you.
I cannot answer, but maybe in few months. Why not?
Okay. So thank you and
thank you.
Mes congratulations, c'était très bien. Hein?
Merci.
Any other questions?
May I make a comment and a question?
Yep.
Concerning the eccentricity, yes, you said that they are presumably quite small.
Yes.
But as it can be seen in other systems, that they are small, but not so small actually. And actually the forced eccentricity is related with the inverse of the frequency ratio of the commensurability.
Yes.
So trying to evaluate how far the system is from exact commensurability could be an indication of how big are the forced eccentricity, and so to give an independent indication about the stability of the system.
Yes, that's something. I don't know if you see the plot here.
Yes.
Yeah. Okay. So yes, that's something. For example, we can do by this angle are in libration around some given value, and this value depends on the eccentricities in the masses of the planets. So maybe it's a way to have information about these eccentricities and these masses. And here it's just one simulation, but we can try I don't know what can we do, because with the current data, the data that we have for the system, it's impossible to do more than that. But we can maybe yes, maybe you can try to do something else, is to start with the average motion, the average problem, and to try to compute, to find where are the fixed points, as you do in the case of Laplace, only one Laplace resonance. It's easy to do in this case, but here with this chain, it's not very easy to do it, but we can, I think, to solve the some equations and to find the location of the of fixed points in these three angles, and it will give the values of the forced eccentricities at the equilibria also.
Yes, yes, but excuse me, there is a puzzling aspect here in this plot, because the third angle librates around more or less 75 degrees.
Yes.
And this is actually a little puzzling as an equilibrium position, but maybe it reflects some asymmetry of the problem.
For example, if you consider the problem of the Galilean satellites, you have just one Laplace angle, and you show easily that the equilibria correspond to 0 or pi.
Exactly. Yeah.
But in this kind of system here with I think. If you consider a chain with 3 planets on a chain, if you have between the two, the planet 1 and the planet 3, if you have mean motion resonance, which is also of order 1, which is not the case in the Galilean system, here you have fixed points that are not symmetric. You have something that is different from 0 or pi, and which depends on the masses of the planets.
Okay. Yes. This could be.
You have a very interesting situation that are non-trivial fixed point values. And here we are in this case, of course. Maybe so. The average values of the libration can give an information about these masses and these eccentricities, but we have to understand the average problem before, I think.
Okay, thank you.
Okay. I think there is time for one quick question. Okay. Otherwise, I thank again Philippe for the very nice talk. And the next seminar will be the 29th of April about Federica Spotto, and it will be announced on the mailing list and on the website. Bye.
Goodbye.
Bye. Thank
Goodbye.
you.
Bye.
Bye.
Bye, everybody.
Everyone.
Ciao.